Hi, students. This week we're going to finish chapter 10, which is the rest of the material on radicals. So remember radicals, they're sometimes called radicals or sometimes they're called roots, like square roots, cube roots. Those are all radicals, okay? Radicals with the same index and the same radicand, meaning the same thing inside, are called like radicals. So over here you can see we've got an index. That might be a 2 or 3 for a squared root or a cubed root, and then the radicand is what's inside, right? So both of these things have to be the same for two radicals to be considered like radicals, right? We can add like radicals in the same way that we add like terms in algebra, just kind of using the distributive property. So for example, if we have a 2x plus 5x, we call those like terms because they both have the same variable raised to the same power. So we use the distributive property to say that there's 2 of these, there's 5 of these, so we add the 2 plus 5 of these things, and we have 7 of those. It's the exact same process with radicals. Just be careful because you're not as comfortable using them. So you have to make sure you have like radicals, which means the index is the same and the radicand is the same. So the square root of 3 and the square root of 3 are identical. Those are like radicals, so we can add them together. We've got 2 of these square root 3s and we're adding them to 5 of these square root 3s. So we've got 2 plus 5 square root of 3s gives 7 square root of 3s. Okay, so those are like radicals and we can add them. Something over here like this 4 root 5 plus 4 cube root 5, these are not like radicals because the index is different. We cannot add this. These are as simple as this expression can get. Okay. Let's come over to our whiteboard, and I'm going to do these 4 examples for you guys so that you can get an idea of how to add and subtract rational expressions. And for the most part, when we are adding, subtracting, or multiplying radical expressions, really what we're doing is simplifying. Okay, so there's lots of different ways to simplify. Usually that means do the addition and subtraction, but also simplify any radicals we have and simplify any fractions we have. Okay, so let's take a look. Let's pop over to my whiteboard. There we go. All right. So our first example, we have square root of 45 over 3 minus root 5 over 2. So initially, when you see the square root of 45 over 3 minus the square root of 5 over 2, you can approach this in a few ways. We could start by just saying, hey, we've got a fraction subtraction problem. We need a common denominator if we are going to combine this into one fraction. We could start there. We could also start with just looking at our radicals and seeing if the radicals themselves could be simplified at all. Either way is a good place to start. Let's start by just combining this into a single fraction so that we can deal with the radicals later. We've got a denominator of 3 and a denominator of 2. So our common denominator, or our LCD, is going to be 6. Oops. The LCD is the 6. So that means I need to multiply my first fraction by a version of 1 that turns the denominator into a 6. So that's going to be a 2 over 2. And I need to multiply my second fraction by a version of 1 that turns that denominator into a 6. So it's going to be a 3 over 3. So once I've done that, my two fractions look like this. We've got a 2 root 45 over 6 and a 3 root 5 over 6. We add those guys together And we're going to get 2 root 45 minus 3 root 5. So we've got 2 root 45 minus 3 root 5 over. Now we have to see, can we add these two terms that both contain radicals? In order to do that, they need to be like radicals. And it doesn't appear at first that we have like radicals. But this root 45 can be simplified. And so let's just take a look at what root 45 is. A square root of 45 is the same thing as the square root of 9 times 5, which is the same thing as the square root of 9 times the square root of 5. And we know that the square root of 9 is actually 3. So this square root 45 can simplify to a 3 root 5, right? So now that we know that, we actually have a 2 times 3 root 5 minus 3 root 5 over 6, okay? So 2 times 3 is 6. So we've got 6 root 5s minus 3 root 5s. And in the end, we're just going to have 3 root 5 over 6. And then very last, we want to simplify this fraction. The 3 over 6 will simplify to 1 over 2. And so our final answer is going to be root 5 over 2. All right. So notice what we did here. We did this subtraction step by finding the LCD common denominator. Once we had a common denominator, we did the subtraction, and then we looked at our radicals to see if we could combine these terms. In order to combine the terms, we first needed to simplify the radical. This square root of 45 is actually 3 root 5. If you wanted to do that before, we could have turned this square root 45 into a 3 root 5 in the very beginning. That would be totally fine to do it in that order as well. But once we did that, we realized we do have like radicals. We perform the subtraction, and then finally always simplify your fractions. All right. So that was our first example. Let's go on to the next example. So our second example here is the third root of 24 minus 4 times the third root of 81 plus the third root of 3. So we don't have to worry about fractions here, but if we want to combine these three terms, they're going to have to be like radicals. So before we can determine if they're like radicals, we'll need to simplify those radicals. So we're going to simplify our radicals by factoring what's inside and seeing if we have any perfect cubes, because these are cube roots. So we need 3 identical factors inside of our radical in order to take the cube root. So let's look at 24 is 8 times 3. So 24 is 8 times 3. And we know that 8 is a perfect cube. In fact, 8 is actually 2 to the third power. All right, so that guy's our perfect cube, and we can pull him out. So the cube root of a perfect cube, or the cube root of 8, is 2. So we've got a 2, cube root 3. Okay. Now let's look at our second term here. That 4 stays out front. 81 is 9 times 9, and 9 is 3 times 3. So 81 is basically 4 factors of 3, but we are just looking for 3 factors. So I'm going to separate one of these factors of 3 off. So I'm going to rewrite this as 3 to the third times 3. Okay, I do that so that I can then take the cube root of this 3 to the third is going to just bring a 3 outside. So I've got 4 times now the cube root of my 3 cubed is just a 3. And then I've still got this last 3 inside my cube roots here. Okay. So we've simplified that second term. And if we want, we can even say this 4 times 3 is 12. All right. And now let's last term, it's the cube root of 3. There's only a single factor of 3 here, so it will not simplify. Okay. Now we see these are all like terms. We have 2 of these cube roots of 3. We have 12 of these cube roots of 3, and we have 1 of these cube roots of 3. So now what we are really doing is we're saying 2 minus 12 plus 1, because that's what all our coefficients say, of these cube roots of 3, right? So 2 minus 12 plus 1 is going to be -9 cube root 3. All right, guys. So that's how you add and subtract radical expressions. It's all about working through simplifying those radicals, seeing if you have like radicals, and then adding up how many of each of those like radicals you have. Right. Now let's go on to the next question, or the next example for you guys. So our next example is the square root of 27x minus 2 times the square root of 9x plus square root of 72x. Let's start by simplifying each of these guys properly. 27, 3 times 3 times 3. So this is really the square root of 3 squared times 3x. Okay. And 9 is 3 times 3, so 3 squared times x. And 72 is 9 times 8. So that's 3 squared times 2 squared. Oops. Well, 8 is 2 to the third, but I'm going to just put 2 factors of 2 together and then another factor of 2 here. So you guys can go ahead and check. 3 times 3 is 9. 2 times 2 is 4. So 9 times 4 is 30. 36 times 2 is indeed 72. So this is 72 completely factored out, but I just separated the 3 factors of 2 into 2 factors of 2 because we're going to take a square root, right? So now let's pull out all our perfect squares outside of our square roots. So we've got over here a 3 root 3x minus 2 times 3 root x plus, we're pulling out a 3 and a 2, but that 2x is stuck inside, okay? So notice what happens as we pull stuff out. I have a 3 squared here, but when I take the square root of it, I just have a 3, right? I have a 3 squared and a 2 squared. So when I pull it outside of this square root symbol, I'm taking the square root, which makes it just a 3 and just a 2, right? Same thing, when I take this 3 squared outside of the square root, I just get a 3. So be very, very careful that when you have these factors that repeat as many times as you need them, here we need 2 repeat factors to get out of a square root. Remember, when you take them outside the square root, you actually have to evaluate that square root and square root them, okay? Make sure you're changing those exponents when things come out of their square roots, right? Now what do we have to look at here? We've got 3 root 3x. We've got 6 root x, and we've got 3 times 2 square root 2x, right? None of these are like radicals. They are all different radicals, and we cannot add them together. We cannot add them together, so we are just going to them in their simplest form. So we've got 3 root 3x minus 6 root x plus 6 root 2x, right? They do all contain a root x. So one way that we could rewrite this is 3 root 3 minus 6 plus 6 root 2 times square root of x, right? They all contain a square root of x. Or if we wanted to factor off that factor of 3, we could do that. We could say we have square root of 3 minus 2 plus 2 root 2 times 3 root x. So these are all the different ways that you could factor it if you wanted to, but your correct answer will just look like this, right? Just notice that each term has a factor of 3 and each term has a factor of root x. So if you wanted to factor it, you could do that, right? So that's what happens when things are not like terms. Be very careful because these things look so similar, but they're not, right? The different radicand means that we cannot add these 3 terms. Okay. All right, let's go to our final example for this section. Our next example is the cube root of 6y over 125 plus 3 times the cube root of 6y. Okay. So right now we have fractions, we have different radicals. Let's first just simplify these fractions that we have, because you guys might not necessarily see this, but 125 is actually 5 to the third. So we can take the cube root of this 125. And if you prefer, we can rewrite this fraction as the cube root of 6y over the cube root of 125, right? Plus 3 times the cube root of 6y. Now this cube root of 125 simplifies to just 5. That's because 125 can also be written as 5 to the third. Now we've got 3 factors of 5 inside a cube root. So we just want to take a third of those factors essentially. So this whole thing simplifies just to 5. So let's rewrite that as just 5. And now we'll ask ourselves, can we add these terms? Are these like radicals? And they are. We essentially here have 1/5 of a cube root of 6y, and we're adding that to 3 cube roots of 6y. So as per the distributive property, it's going to look like this. 1/5 plus 3 of these cube roots of 6y. So we have 1/5 plus 3 of these cube roots of 6y. This is our 1/5 because we're dividing the cube root of 6y by 5. So we have 1/5 of it. And this one is 3 of them. And they are like radicals because the radicals are identical. The index is 3 and the radicand is 6y, right? So now we can add this together, the 3 plus 1/5. What we need to do is give these guys a common denominator, which is going to be 5. So I'm going to multiply this 3 times the fraction of 5 over 5. So we're going to have 15/5. And when we add them together, we're going to get 16/5 of these 3 cube roots of 6y. All right. So that's our answer there. Don't be overwhelmed when you see fractions. Remember, we have that quotient property that allows us to split up the numerator and the denominator under the radical, so we can simplify them separately. All right. And don't be intimidated when you see a fraction like this. You can separate the fraction really as 1/5 times this cube root of 6y. So let's head back to our whiteboard. Right here. Okay. So that was adding and subtracting radical expressions. Let's take a look at multiplying radical expressions. So when we multiply radical expressions, we do it just like how we multiply other expressions. And then we have to use the properties of radicals and of exponents just to help us simplify in the end. So when I say we multiply just like regular expressions, I mean we use the distributive property to multiply out over addition. All right, so let's go through these examples on our whiteboard. I'll start with the square root of 3 times 5 plus square root of 30. And the nice thing about when we multiply radical expressions is we can multiply together any two radicals. If the index is the same, that gives us room to use the product property. All right. So let me share with you my whiteboard. And we will go to our first example. So we've got the square root 3 is being multiplied by 5 plus the square root of 30. Okay. Because we have parentheses here, we need to distribute that square root of 3 to each of the two terms inside parentheses. So that's going to be square root of 3 times 5 and the square root of 3 times the square root of 30. So that's going to give us 5 root 3 plus square root of 3 times square root of 30. All right. And now we have these two square roots, the square root of 3 and the square root of 30, and they can be combined to just the square root of 3 times 30. Okay. And if we want, we can say, well, 3 times 30 is 90, right? But before saying 3 times 30 is 90, maybe it's easier to actually look at all the factors that we have. And really, we just have one of those factors of 3 pulled out. Remember, we are inside a square root, so we are looking for pairs of identical factors. So if I can get another factor of 3, I can simplify that square root. So we've got 5 root 3. And then 3 times 30 is really 3 times 3 times 10. And 10 is 2 times 5. So we see right here, we actually do have two pairs, two identical factors. So we've got a square. That 3 times 3, we could call that a 3 squared. And we can pull that out of this square root. So this pair of 3s inside the square root is going to become a single 3 outside the square root. The 2 times 5 has to stay in as a 10. Right. So now we have 5 root 3 plus 3 root 10. These are not like radicals, so we cannot add them. And that is our answer. So when we're multiplying our radicals, we're just using the distributive property and then doing any radical simplification that we can do. And then finally evaluate whether or not you can do any addition or subtraction. We cannot. So this is as simple as our answer can be. Okay. Let's take a look at another example here. So our next example is the cube root of 2 times the cube root of 4 plus 1. And notice that just the 4 is inside the cube root. This plus 1 is a different term and it is not inside of that cube root. Okay. You might say, oh, but 4 is a square. That doesn't matter because we need 3 factors, 3 identical factors in order to take a cube root, and 4 is just 2 times 2, okay? But once we multiply out, we're going to multiply this cube root of 3 times the cube root of 4, and we're going to multiply this cube root of 2 times the 1. So we get the cube root of 2 times the cube root of 4 plus 1 times the cube root of 2. Right. Now we're going to work on simplifying this stuff using the product property. All right. That can all come under 1 cube root, 2 times 4. And we can multiply 2 times 4 and say that that's 8. But we also know that 8 is 2 times 2 times 2. So this cube root of 2 times 4 is the same thing as the cube root of, let's say, 2 cubed, right? Because 4 is 2 times 2. We're multiplying it by 2 again. So we have 3 factors of 2 here inside of a cube root. And so that stuff's all going to be able to get simplified. Let's not forget that we have this other factor of, or this other term of cube root of 2, right? So when we put all that stuff together, we've got the cube root of 2 cubed, and that is just a 2. So this whole thing right here just becomes the 2. But we still have that other term that is cube root 2. So here is our final simplified answer, 2 plus the cube root of 2. Okay. Let's go to our next example here. So our next example is the square root of 2x. And notice the x is under the square root, minus 5 times the square root of 2x plus 5. So now we have to use FOIL, where every single term in here needs to get multiplied by both the terms in here. So FOIL is just a way to remember this first term has to get multiplied by both of these terms. This second term has to get multiplied by both terms. Okay. So we'll do that. We're going to have root 2 times root 2. Sorry, root 2x times root 2x. That's our first terms. We're going to have the root 2x times 5. Those are our outside terms. And then we're going to have the negative 5 times the root 2x. Those are our inside terms. And then we're going to have the negative 5 times 5. Those are our last terms. Okay, so now we've got 4 different terms, and we're going to go through and actually do that multiplication within the terms. So I'm going to multiply these things. And then we'll see if we have any like terms that we can add together. So notice square root of 2x times square root of 2x is actually 2x squared. So this whole thing just simplifies to a 2x. Maybe I'll rewrite it. We can rewrite it as square root of 2 squared x squared if you want. Or 2x in parentheses squared, but that all becomes just a 2x. Okay. So that term becomes a 2x. Our next term, 2x times root 5, we're just going to rewrite that 5 times square root of 2x times 5. We're just going to rewrite that as 5 times the square root of 2x, because we like to write the constant, what's this guy called that we're multiplying by? The coefficient. We like to write the coefficient first, just so you don't get confused and think that it's under the radical. Okay, and it's multiplication, so we can write it in whatever order we want. Now over here, we've got the negative 5 square root of 2x. That's already simplified, and then we're subtracting 5 times is 25. So can we combine any of these terms? Are they like terms? And in fact, they are. We've got a 5 root 2x and a negative 5 root 2x. So this root 2x is the same. So we've got 5 of them, and then we're going to subtract 5 of them. So these two terms actually cancel out. We've got a positive and negative of identical terms. And so we're just left with the 2x minus 25. And that is completely simplified. So take a look at what we started with and notice how nicely it's simplified, how both of these middle terms, these what we call cross terms, canceled out. These two pairs are almost identical. The only difference between the square root of 2x minus 5 and the square root of 2x plus 5 is the sign. And because we had a negative sign here and a positive sign here, that caused these two terms to differ just by a positive and a negative. And that's why they canceled out. Right. These two terms we're going to talk about later. They're what we call conjugates. Right? They're a pair of numbers that are differing only by that sign they're combined under. So let's do our last example. We have the square root of x plus 2. That plus 2 is inside the square root. Then we're going to add a 3 after the square root, and we're going to square it. The best way to approach something like this, whenever you have multiple terms all being squared, is to rewrite out what this squared really means. This squared is essentially saying we've got the square root of x plus 2 plus 3 times the square root of x plus 2 plus 3. All right, so that's what that squared means. It means we multiply this whole thing by itself again. So let's take a look at, we FOIL it out. We've got the square root of x plus 2 times the square root of x plus 2. So we're going to call that the square root of x plus 2 squared. That was these first ones. Now we've got the square root of x plus 2 times 3. So that's 3 times the square root of x plus 2. Then our inside terms, we've got 3 times the square root of x plus 2 again. And our last terms are 3 times 3. Now let's go through and simplify these 4 terms we have. The square root of x plus 2 squared is just an x plus 2. 3 times the square root of x plus 3, plus 2, should be 2 in there. And then we've got another 3 times the square root of x plus 2. So in total, the 3 of these plus 3 of these is going to give us 6 of these square root x plus 2s. Right? And then 3 times 3 is 9. So now we'll look at all our terms. We've got an x, a 2, a 6 times square root of x plus 2, and a 9. The only like terms we have here are the 2 and the 9, so we can add them. 2 plus 9 is 11. And so we've got our 11 plus x plus 6 root x plus 2. And that is as simplified as we can get because we have 3 terms. None of them are like terms. Our square root is completely simplified. And that's our answer for that last problem. All right, so that is, that's how we simplify all these radical expressions. That's how we add them, subtract them, multiply them. And it's just a lot of simplification steps and all the algebra that you guys already know. Keep track of everything. Really make sure you understand what is radical and what is not inside a radical. And then make sure you are correctly simplifying your radicals. Okay. That is section 10.4. Good luck on your homework.